Hi guys, so before doing the math for the simple harmonic motion, I just want to review what we did last time. So we talked about elastic objects that can oscillate about their equilibrium, and in most cases, and even to a very good approximation, we have that the if you have a restoring force, so it's a restoring force, or it could be a restoring torque. That means when you are twisting something like a wire, like I show you the example last time, like in that case, you have a wire here, you twist and then you let go, it's going to oscillate and it will also follow a simple harmonic motion. So in those cases, when the restoring force or the restoring torque is in magnitude, okay, is proportional, so that's just a constant, to the displacement. So displacement could be y, that will be displacement about the equilibrium, or it could be cx. For a torque, it could be proportional to the angular displacement. So remember, like when we talk about the bungee jump, right? So it's gonna be, let's say this is the y here, this is the equilibrium, and it's gonna be the cord is gonna stretch, and the restoring force here is in this direction here. Acceleration is in this direction here, plus, so he's gonna jump here, and because the cord is stretching, the restoring force is opposite, right? So it will be proportional to the displacement about the equilibrium. So in that case, we have a simple harmonic oscillator with a simple harmonic motion, right? And we've seen that in those cases, then we can say that the restoring force equals Newton's second law, the mass times the acceleration. So in that case, the force is along the y and the acceleration is along the y. So I'm going to have minus c, a constant, and then the displacement will be y equals a m times the acceleration. So you always end up with an equation of this type here. So you have the acceleration here, you have the displacement here equals 0. So this is the equation of a simple harmonic motion. And then you can divide by mass here everywhere, and you get this. So this is, we'll see that in more details, but it's a differential equation of second order. But when you end up with this type of equation, then you always have that coefficient here in front of the displacement. That here, it's going to be the angular frequency square. Okay, so that's going to be C over M. Example, if you have a spring, then you're going to get that omega 0 square equals the square root of, and then here you have K, and here you have the mass. Okay, and then of course if you square, you get K over M. That's for a spring. If you have a pendulum, then you also have the same type of equation, except here you have a angular or rotational acceleration because it's going to swing back and forth. And then here you also have, I think it's G over L times theta equals 0. So we have that omega 0 squared equals G, which is gravity over L. And we talk about that. So as long as you have this type of equation, then you know that you have a simple harmonic motion, right? So let's talk about omega 0. So omega 0, it's what it's called the angular frequency. So you can define omega 0 each time you have a phenomenon that will repeat itself over a cycle, right? So omega 0 will be 2 pi over the period. So the unit is rad per second. So again, it's called a period. The unit is in seconds. So that will be the number of seconds for one cycle. And then you have the frequency, which is the number of cycles per second. So which is, the unit is in hertz. Okay, so of course you have frequency equals 1 over the period. You see they are reciprocal. And then you have omega, which is like a frequency because it's proportional here, but with a 2 pi. Okay, so that will be how many radians per second. So example, if you have omega 0 equals 2 pi over 3, what's going to be the period? So the period will be 3 seconds. So what does it mean 2 pi over 3? 2 pi over 3, if you take your calculator, 2 pi over 3 is 120 degrees, right? So it means that let's take a circle here. So let's say something is moving along that circle and at a constant speed, and after 3 seconds it's coming back to the same position. So this is 0, this is pi over 2, this is pi, and this is 3 pi over 2. So what does it mean? It means that in 1 second, it's going to be at here, right? So that's going to be 120 degrees in 1 second. So 120 degrees, it's going to cover 120 degrees in 1 second. So in 2 seconds, it's going to be 240 degrees. Okay. So that's another 120. And then 3 seconds is going to be 360. So that's the meaning of angular frequency. So that means what's going to be the angle swept in 1 second, right? When something repeats itself, you can imagine it's going around a circle, right? It takes 3 seconds to go around. So 3 seconds, it means 2 pi over 3, 120 degrees in 1 second, right? So it's just a way to describe periodic motion. Okay, so each time you have a periodic motion, so you can define the period, you can define the frequency, so how many cycles per second, and you can define the angular frequency. Okay, so let's do now. Okay, so we did all that. So let's do, before going into the math, like describing the motion of a simple harmonic oscillator, I want to do some math. Let's review the math, and then it's going to be easier to understand. So first thing I want you to notice, let's say I have a cosine. Okay, so cosine with x will be the time. So let me show you what I mean. Let's plot a cosine. So let's plot 5 times cosine. And when you want to plot a cosine, you always put a 2 pi here times the variable, which is the time. And I'm going to take 3 here. Let's see what I get. For t between 0 and 15. So that's a typical cosine. I could have done sine, but you see at t equals 0, cosine of 0 is 5, okay? And then the motion will repeat itself. Okay, so you can see here, you can ask yourself, what is the period? So it starts from here, and it could be something that goes down and then up again, and it goes back to the same position here, because that's going to be the time. How long does it take here for that object to go back to the same position? How long does it take here? Can you see here? That will be the time. So the time for one cycle is 3 seconds. So when you want to describe a periodic motion, typically a cosine or sine, you always have here, you're going to put the period. The period here in that case is 3. Okay, so after 3 seconds, it's going to go back here. Another 3 seconds here. That will be 6 seconds. You have 2 cycles. Another 3 seconds, you have 9. 9 seconds, you have 3 cycles. And then another one, you have 4 cycles, and so forth and so on. So a cycle will be, you go up, you go down, and you go back to the same place. Okay, that is a periodic motion. Okay, you can start here at t equals 0. The thing is going to go down and up to the same place. Okay, and I have a cosine. So each time in math, you have a cosine function. Here, you're going to have the period. Okay, now you can do the same thing with a sine. Doesn't matter. A sine will be shifted by 90 degrees. So if I put a sine here, you see that at t equals 0, the displacement here is 0. And then you go up, and then you go down, and then you go back to the same place. That's also the period, 3 seconds. So you notice here that the amplitude is 5. Okay? So when you want to describe a cosine, here, you have to change only 2 things. The period that goes here and the amplitude that goes there. So you see, if I put 10 here, you see that the amplitude is 10. So it goes, the displacement here along that axis goes from 10 to minus 10, right? So it goes up and it goes down, it goes to the same place. This here will be always the period. So if I put a 2 here, and let's say 2 between, 8. So you see here how neat this is. Now the period is 2. The amplitude didn't change, and the period is 2. So let's go back to a cosine. Doesn't matter. You can take sine or cosine, does not matter. Okay? So you see the period is 2 now. Go back to the same place after 2 seconds. So let's go back to 3. You just have to remember. Okay. So if you want to describe this function here, so again, I lost my... Okay. So if I look at this equation here, so let's look at this equation here. So let's say it's a function of time, y over t. So it could be something, moving up and then down and then up and down. Okay, so just along the y, goes up and then it goes down and then up and it goes down. But now I spread over the time here. The amplitude here is going to be 10. Okay, so it starts here and it goes this way, that way, this way, that way. What we have here, this is the amplitude. What we have here, and let's go back to the 3. Let's go back to 3. Okay, so what we have here is called a period. Okay, so here I have 3. So you have here, that's going to be the period cosine 2 pi over 3. 2 pi over 3 times the time. And the period is 3 seconds. So did you guess what is that coefficient here? That coefficient is just the angular frequency, 2 pi over 3. And the unit is going to be rad per second. Now, if you want to find just the frequency, it's going to be 1 over 3, so 0.333 hertz, which is cycles per second. Okay? And the period here is the period here, not the period, sorry, the amplitude is 10. Okay? So if someone give you a function, something like this, I don't know, 5 cosine, I don't know, I'm going to put here, 15t, then you know that it has an amplitude of 5, okay? And you know that omega 0 equals 15 rad per second, okay? And so you can find the period, that's going to be 15 equals 2 pi over the period, okay? So the unit is rad per second, so the period will be, you cross multiply, so 2 pi over 15. Okay, so that's going to be 6 divided by 16, and I don't see anything here, so 2 pi divided by 15, period is 0.4. And again, I lost my 0.4 second. Okay, so you know that here will be, the unit will be 5, and here we have 15, we said 15. Is that right? Okay, let's look. Indeed, the amplitude is 5, so 5 to minus 5 at t equals 0 is going to be 5. And 2, you see 1, 2, 3, 4, 0.4. Indeed, the period is 0.4. Okay, so you see how it works? Angular frequency. Okay, so now you know how to decode a cosine, the graph of a cosine function that can be describing a motion, that's something that goes up and down in a periodic fashion. So let's do something else now. You all know what a parabola is, right? So let's trace a parabola. That's a parabola, simple parabola, ever. Okay, and what's happening if in math you want to switch a function, to the right or to the left. So it means I want to take exactly that function here, but I want to shift it in this direction. So to shift a function, let's say you have a function f of x, then that same function shifted to the right, it's going to be f of x minus, if you want to go to the right, you're going to put a minus minus, let's say you want to shift that to 1. That's going to shift the function to the right by 1. That's a horizontal shift. If you want to shift it to the left, so you're going to do f of x plus 1, and it's going to shift that to the left. If you want to shift it up, you just do plus 1. Okay, so let's see. The best way is to do it to understand. So let's see, I want to shift to the right. I'm always put a minus here. Just I'm substituting, I'm replacing x by x minus 1. And you see, I still have a parabola, but shifted to the right. I can shift it more if I want. I can shift it by, I don't know, or less. I can shift it by 0.5, for example. Let's see what's going on. It's going to shift here. 0.5. 0.5 here. Okay. I can shift it to the left. So I can put a plus here. Boom. Shift to the left. Isn't that cool? So let's go back to my cosine. So I had like 5 times cosine. My period is 3, so 2 pi times t over 3. Okay. And let's see what's going to happen if I take the same function. And now I'm going to put minus 2 pi. Let's see what's happening. Let's see what's happening. Five times cosine. First of all, if I shift everything by 2 pi, I should not have any difference, right? So times t over 3 minus 2 pi or plus 2 pi for t between 0 and 15. Let's see if it works. See, I have the two functions on top of each other because cosine whatever minus 2 pi, cosine whatever plus 2 pi is just shifted by one cycle. So you take the whole cosine function, you shift it by one cycle, so you get the same thing. So now let's see if I shift by half of a cycle. So according to what I told you before, here, I'm going to do exactly like I did for the quadratic equation, for the parabola. I'm going to put here times t. I'm going to put t. Look carefully, okay? I'm going to put 1.5. So 1.5 is half of a circle. Half of a cycle, right? One cycle is 3 seconds. Now I'm going to shift everything by half of a cycle. Think of what you should get. So I take this function and half a cycle is, this is 1. So 1.5. I shift everything by half a cycle, by 1.5 seconds. Let's see what you get. Okay. So my original function is this one in blue, cosine. And now in orange, it's the same function, but it has been shifted to the right by half of a circle. Okay, so when you do that, you get the same function but with a minus, right? Because if you add pi, which is half a circle, you see here you have 5 and now you have minus 5. So anyway, you shift everything half of a circle to the right. Okay. But that's hard to see what's going on. We need an easier way to write that down. So instead of putting the time here by which it was shifted, which is half of a circle, I'm going to keep my 2 pi t here, okay? But now I'm going to write the shift in radian. So half of a circle, half of a circle, okay? Half of a cycle, one cycle is 2 pi, so half of a cycle is pi. Okay, so I'm going to put minus pi here. Let's see what I get. Oh, I didn't put the 3 here. Okay, cool. So it's the same thing. You see, in blue you have your cosine, okay? And the cosine has been shifted to the right by half of a circle. So whatever shift you want here, you're going to put here in radian. Okay, so if you want to shift it by one cycle, you're going to do minus 2 pi. Half of a cycle, you're going to do pi. So let's say I want to shift it by 1/4 of a cycle. So that's going to be pi over 2. So you see, it's shifted by pi over 2. And what do we get? We get sine. Okay? Because if you remember from trigonometry, and again, I always lose my so if you remember from geometry, so cosine theta minus pi over 2. This is in radian. It's going to be the same thing as sine theta. Okay? So that's how you shift. Whatever is inside here is going to be the phase. So what's the meaning of this here? So let's take another example. Let's take minus, I don't know what I did here, minus 2 pi. Let's say I shift by, I forgot what example I did, but let's say I shift by pi over 3. So there is a shift here. So it's called a phase shift. And what's the meaning of that? The meaning is that when you take t, so let's say you take t equals 0, what's happening at t equals 0? Then you're going to have the amplitude, instead of being equals to 5, it's going to be equals to 5 times cosine of minus pi over 3. Pi over 3 is 60 degrees. So minus 60 degrees or 60 degrees for cosine, it doesn't matter. If I do cosine 60, I get 0.5. Okay. And 0.5 times 5 equals 2.5. So this is 2, this is 4, this is 5. So 2.5, this is 2.5 here. Okay, so at t equals 0, you have 5 times cosine 60 degrees. Cosine 60 is half. Half of 5 is 2.5. That's what you get. Okay, so this is called the initial condition. So you can shift any function here. You just have to put a minus and the shift that you want relative to a circle. Okay, so one cycle is 2 pi, so that will be pi over 3. If I put a plus here, you're going to shift the other way. Okay, so now this is shifted still by pi over 3, but the other way. Okay, so if you want to find what's the time here, so then you will do you can what you do is, so you can do 2 pi over 3, so that will be 1 cycle, so that's going to be 3 seconds. So 2 pi over 3 in 1 second, in 1 second. So 2 pi over 3 in 1 second, that's the angular frequency. So in if you want to know what's going to happen, pi over 3, so pi over 3. Okay, so pi over 3 is going to be 0.5 seconds. So it has been shifted by, from here to there, that's going to be 0.5, okay, because 2.5, 3, 3.5, I mean, it's hard to see here. 4, 4.5, 5, 5.5, 6. So it shifted by about 0.5. Okay, so let's go back to my example here. And we were minus pi over 3. So pi over 3 is 60 degrees. Okay, so 60 degrees is half of 60 degrees is half of 2 pi over 3. So in 1 second, that here again, it's the angular frequency 2 pi over 3. That means in 1 second, it's covering, in blue here, in 1 second it's covering 2 pi over 3, which is 1/3 of 360. Okay, so pi over 3, it's 0.5. Okay, so the time here, it's on the time scale, it's shifted by 0.5. Okay, so I really recommend that you play with that for a better understanding, because once you understand the math, then the physics is easy here. So let's go back here. Let's the cosine function here. Okay, you see, I can write cosine, so it's going to be cosine 2 pi over 3. Okay, I'm going to factor here, so it's going to be t minus, so I'm factoring out, so here you're going to have t minus 1/2, because when you distribute here, you have 2 pi over 3t minus pi over 3, and that's 0.5 seconds. Okay, so it means that if the period here is 3 seconds, so that means in 1 second, I have 120 degrees. Okay, so 2 pi over 3 in 1 second, that's my omega. So pi over 3, it's going to be 0.5 seconds, right? So everything is shifted by 0.5 seconds here. Okay, so you can play with that. Okay, you can shift this way, you can shift that way, you can do the same thing with the sine. Okay, so how to connect that to the simple harmonic oscillator? So imagine now, so this is an app I found here, you can go on that website. So imagine now I have I have the motion, I have a circular motion, right? imagine that you have a particle going around a circle, okay? And the period is, again, I'm going to make that period 3 seconds. Okay? So if I take that here, if I take like something going around a circle, so it's going around a circle at a constant speed. Okay, so that means the angular speed is, I want that to go at a speed of 2 pi over 3 rad per second. So it means it's gonna go at one revolution. It's gonna take 3 seconds, right? So in 1 second, it's covering again, it's gonna be 120 degrees. So that's 120 degrees for 1 second. So that's the angular speed, but you see that motion is going to repeat itself. So this is also equals to the angular frequency. So at a given time here, I can find here the projection on the x-axis here. That projection here is going to be the cosine. So let's say at a given time, the particle is here. So you have something going around a circle. And you see, that's going to be the projection here. Okay, so that's going to be your cosine. So it's going to go here. That's going to be the cosine. And then it's going to go here. And it's going around the circle. So that angle here, that's what we call the phase. Okay, so this is my x-axis. So what I'm doing here is polar coordinate. And you see x as a function of time, it's going to be the amplitude here. So let's say the amplitude is 5 cosine, and the phase here, I'm going to say it's 2 pi over 3 times t. So let's see, what do I get? Of course, you can do the sine as well. So that will be the y coordinate. That's x of t. This is y of t. So that's going to be 5 sine 2 pi over 3t. So let's do that. So the amplitude is 5. I'm not going to worry about that. Omega is 2 pi over 3. So if you take your calculator, so 2 pi is going to be 2 times pi, okay, divided by 3, and you get about 2.1 rad, okay? And that's how many up and down I want. So let's see what's going on. You see that cosine function, so that cosine function that repeats itself every 3 seconds is just the x coordinate, okay? It's just the x coordinate of something going, I know, let's say it's a particle here going around a circle, okay? So it's going around a circle. It takes 3 seconds to go around. And if you project, if you take the x coordinate, that's when you get your cosine here. Okay? So sometimes it's called a phasor diagram. And we're going to see why it's convenient to use this visualization instead of that one. Okay? So for example, now if I put a theta here, that theta here will be my shift. Okay? By how much is going to be shifted. So now let's try 90 degrees here. So 90 degrees is 1/4 of a cycle. Okay, so 1/4 of a cycle. So what does it mean? So again, 1/4 of a cycle, if the period is 3 seconds, so it takes 3 seconds to go around for the particle here. It's going around like this at a constant speed. So 1/4 is this, okay? So from here to there. So 3/4 is 0.75 seconds. So if I put theta here equals to 90 degrees, but 90 degrees to the right, so it should shift to the right. And indeed, you see the maximum here used to be there, and now the maximum is at 0.75 seconds. So what it did, it moved the function to the right by 90 degrees or by 0.75 seconds. What it just means, it means when you start the stopwatch, okay, t equals 0, then you don't get maximum, you get 0.75. So when you start the stopwatch here, 90 degrees, sorry. When t equals 0, you have cosine minus 90, which is 0. When you start the stopwatch here, you have, so when you start your stopwatch, you are minus 90 degrees here, so it's there when you start your stopwatch, and the amplitude equals 0. Okay? And then it's going up. So everything is shifted to the right. So I hope it's clear. And you can see that here I have another example. Now you have the sine function here, and it's been shifted a tiny bit also to the right, because when you start the motion, you start here, when you t equals 0. Okay? So these phasors are used for electronics, for example. So anyway, let's go back. Why is it relevant here? So here, have this slide. So that slide comes from the book Johnson and Cutnell Physics. You see that if you have an object going around a circle, okay, in a periodic fashion, imagine you have a light here, and you project that motion along a paper. What you're gonna get? You're gonna get the x. This is the x-axis. You're gonna get a cosine function here that you can write this way. A is the amplitude. Omega is the angular speed or the angular frequency. So in that case, it's gonna be the same. Now, why is it relevant here? So let's go back to, I have a great video from, I think it's from MIT. So I think it was used, the first time in demonstration by Walter Levin for his MIT classes. So I'm gonna make the connection between the math we just reviewed and the simple harmonic motion. So it's a great demo. So here I have a spray. And spray, if you are doing painting, and here you have a spring. Okay, so we do have a simple harmonic oscillator. I have a vertical spring here and have a load. So he's gonna displace it to a given amplitude, and then he's gonna let go. So it's gonna go up and down, like we have seen, and it's an oscillator. So we want to find out the displacement about the equilibrium along the Y. What it's gonna look like. Okay? So what does it mean? It means that any simple harmonic motion, when you're going to describe the displacement versus time, you're going to get a cosine. Okay? A cosine or a sine depends when you start the stopwatch. You can define the amplitude, that will be the amplitude of the oscillator. You can define the period. You can define the angular frequency, and you can define the frequency. So how many times it's going in 1 second? How many cycles per second? So if I look at this here now, you see here it's about the equilibrium position. That's my 0. That's I don't know where you want to start. T equals 0, let's say it's here. So t, that's the time. That's my displacement y. That's going to be the amplitude of the oscillator. Okay, so it's between a and minus a. Okay, so you see at t equals 0, when you start to stopwatch, it's going to be a. And that here, you're going to define 1 cycle. So between here and there, that's going to be the period. Okay, in second. So the number of cycle per second, the number of cycle per second is going to be the frequency. So how do we describe that displacement as a function of time? It's going to be y as a function of time. It's going to be a, the amplitude, cosine omega t. Okay, and then you can have, if you can add a phase shift, depending when you start a stopwatch. But that's the idea. And omega is always equal to 2 pi over the period. Okay, and you can visualize this motion. You can visualize this motion if you take so if you take a particle here, if you take your mass that is going up and down, everything will be the same if that mass here is going, describing a circle at a constant speed, at the speed omega, right? And you are looking at the projection along the x-axis, so you are just looking at the x displacement in that case, and it's going to be described that by that equation here. So I have other, let's say I have a simulation here. So you see, you have an object moving at a constant speed along a circle. But look here, if you have the projection along the x-axis, what do you get? You get a simple harmonic oscillator. So that means that if you want to visualize, the motion of a simple harmonic oscillator, you can imagine that same mass moving around a circle, and then it becomes easier to visualize the phase. Okay, because that angle here would be the phase. I have another simulation, I think, here. Is that do I have open with? It's not going to work. So you see here, if you focus on the right, that will be the projection of the motion on the screen, and you see it's very much like the mass on the spring going up and down, right? So that will be the sine function. So that's one way to visualize the motion of an oscillator. And here, you can look at that. That's a great simulation as well. So the conclusion is that each time you have a simple harmonic motion, then your oscillator, then you can describe its displacement. So it could be the displacement along the x or along the y, or it could be angular displacement. It's going to be always x max, so that will be the amplitude. There will be a cosine here. There will be a omega t plus a phase shift here. Okay, so this is called the angular frequency, so that will be 2 pi over t, and this is called the amplitude. Okay. Here. So each time you have that kind of oscillation, you can define the amplitude, the period, the frequency. And then here, for example, I have a cosine, and that's going to be one cycle. Okay. Now, okay, so just before we talk about the speed and the acceleration of an oscillator, so just to make sure this is clear, imagine you have a spring here and you have a mass. So it's a simple harmonic oscillator, so it's going to go down and up and down. And if you look at the displacement, so here the displacement is x, but it could be y. If you look at the displacement as a function of time, it's going to describe a sine function or a cosine function. Doesn't matter which one you pick, right? You have to be very careful at t equals 0 where the mass is. Okay, so let's say you are projecting along the y-axis here. So you will get you will get a projection. So that, like everything happens like that mass here. Everything happens like it's moving around a circle at a constant speed, and you are projecting the motion along the y-axis. And if you do that, you get a sine function. If you project here along the y-axis, you're going to get a sine function. So here it's a sine function. So why are we using this? Because when we do more advanced physics here, so you see here what you have inside, it's called the phase. And the phase will be just this angle here. That will be your phase here inside the cosine or inside the sine. And it's easier to compute the phase using that circle there, right? So that will be your phase here. But the phase will be in radians. And you see that sometimes at t equals 0, you don't start your stopwatch when it's here, but when it's there. So you see in that case here, you have a phase shift. So it means that your sine function has been shifted horizontally. Okay, so I hope it's clear now. I have a lot of simulation. I have found another simulation on Wikipedia. So you see you have a mass here. It's moving around a circle at a constant speed, but you can project the motion along the x-axis. So it will behave like a simple harmonic motion, and you have a displacement. Displacement is x, and you can describe that as a cosine. Now, if you project along the y-axis, then you have a sine. Okay, and that angle here that you have at a given time, that's going to be the phase. Okay, so again here, let's look at this one. Maybe this one is a nice one again. So here you have your oscillator. So it could be a spring, a mass on the spring, and it's just the projection of that mass going around the circle at a constant speed. Okay, so talking about speed, let's go back to here. You see, this is our mass going up and down. So you have the displacement. It's going to be minus a, 0, plus a, and we've seen it describing a cosine function or a sine function. But look at the speed. So the speed here is going to be 0. Here it's 0, it's going to increase, and then it's going to be 0, and then it's going to increase maximum, and then it's going to be 0, and then it's going to increase maximum, and then it's going to be 0. So the velocity of an oscillator should be also described by a sine or cosine function. Look at the acceleration. The acceleration also has the same behavior, right? So it's 0 here, and then here it's maximum. So acceleration works like with a restoring force. So when it's when it's all stretched here, the speed is 0, the acceleration is maximum. Then when it's going through the equilibrium, the acceleration is 0 and the speed is maximum. And then it's squeezed all the way up, the velocity is 0 and the acceleration is maximum. So we can see that here. So if I look at the velocity, and again, I'm going to imagine you have a mass moving at a constant speed around the circle. And let's say if I can make it slow down. If I project on that screen here, look at the velocity, right? It's going to be 0 here, maximum 0, maximum 0. So it will also behave like a cosine or a sine function. Okay, so now if I look at the acceleration, I'm going to again have the same. So acceleration in that case, it's going to be a acceleration because it's moving around the circle. So it's moving along a circle at a constant speed. Okay, so it's a circular motion. So it doesn't go faster, it doesn't go slower, but I do have an acceleration. This is called a centripetal acceleration. But look at the projection here. So if I slow it down, see, I have the same behavior, maximum 0, maximum 0, maximum 0. Conclusion is that the acceleration, when you have a simple harmonic motion, also should follow a sine or a cosine. So let's look at the math now. So this is again our oscillator. So it's in a simple harmonic motion. So at t equals 0, it's all the way there. So the spring is all stretched. The velocity equals 0. When it's going through its equilibrium position, you have the maximum velocity and it's pointing to the left. So it's negative. And then the spring is compressed. So velocity equals 0. And then it's coming back. And in that case, the velocity is maximum, but it's positive. And then it's back to its equilibrium position. So if, again, you have a mass here, so that mass here going around a circle at a constant speed. So the speed is constant. Okay, so the period is the time to go around once. And imagine you have light here. You project that mass here, like I showed you last time, on the screen, you're going to see the same motion. So it means that at t equals 0, let's see, I have like a screenshot here. So at t equals 0, it's going to be here. So t equals 0, it's going to be here. So that's going to be position 1, position 1. Okay, so you see that the velocity here is tangent to the trajectory, and you see that the x component here, you see x component here is 0. So the x component of the velocity equals 0, okay? Because here, see the x component equals 0. That's at t equals 0. Then t equals 1/4 of the period. So here, when it's there, going through the equilibrium position, you see the velocity here is going to be maximum. Okay, so that's going to be maximum, and it's going to be negative. Okay, the speed is the same, and then again, it's going to keep going here when it's half. So it's half here, half for the period. You see that it has no x component, so the velocity equals 0, the x component. And then here it's going to be 3/4 here. So t equals 3/4 of the period. And again, the velocity here is max, but it's positive here. The velocity also was max, and it's the x component, it's going to be negative. And then here, x component equals 0 for time equals the period. Now, you see at that position here, in between, that will be the velocity. And what you want is to take the x component of the velocity. So that's how it works, right? So you can visualize the motion of a harmonic oscillator by imagining, just imagine that you have that mass going around a circular motion, following a circular motion at a constant speed, right? So that was the simulation here. I don't know where I found that simulation, but you see, this is the circular motion. It's going around at a constant speed. And if you project on the screen, you get that harmonic oscillator, right? If you project. So that means in that case, you are using the y component of the velocity. See here, velocity is going to be maximum here. Here, velocity equals 0. So the displacement is also a cosine function. So I forgot if I told you, but that will be the velocity of oscillator. So what do we know? We know that the displacement of a harmonic oscillator, simple harmonic oscillator, the displacement, so that's the displacement about equilibrium, it's going to be equals to the amplitude, and then you have a cosine omega t, and then here you have a phase shift. It depends on its on the initial condition, right? So if you imagine that you have your mass here going in a circular motion, for example, if you start your stopwatch at that position here at t equals 0, so at t equals 0, that should be your x, then that here, that will be your phase here when you start at t equals 0. Okay, so how do we find the velocity? So do we find the velocity? Remember, if you took calculus, it's just the derivative. So dx over dt. So you take the derivative of cosine, it's going to be a sine, but you have to take omega out. So it's going to be this. Okay, so that here will be the V max, the maximum velocity. Okay, and it's going to follow a sine function. Now, if let's look at an example first, and I will go through a lot of examples. So let's take an example here. So you have the diaphragm. It's a loudspeaker, and it will behave like a simple harmonic oscillator. So it will be pushed and pulled with a magnet. It's an electromagnet, so it's going to be doing this. It's going to vibrate about its equilibrium. It has an amplitude A, and they want you to find the maximum speed. Okay, so uh, so let's see what we have. We have the frequency. So the frequency is 10 to the third hertz. The angular frequency, and we talk about that a lot, it's going to be 2 pi times the frequency, or 2 pi over the period. The unit is rad per second. So how many rad for 1 second? So it's going to be omega, it's going to be 2 pi times 10 to the third. Okay, so Vmax, it's going to be the amplitude times omega. So Vmax, it's going to be, I'm dyslexic here, it's going to be the amplitude, which is 0.2 millimeters 10 to the negative 3 times 2 pi times 10 to the third. So that goes away, because 3 minus 3 is 0, 10 to the 0 is 1. So Vmax, it's going to be 2 pi times 0.2. And what do we get? Zero point 0.2, 1.3. So you see, this behaves like an oscillator, right? You can have a model here. You can say everything happened like it's like a spring. Here it's compressed. Here the spring is at rest, and then here the spring is stretched. Okay, so where is the velocity maximum? It's gonna be here. Okay, so if you look back to here, so let's look at my velocity. Let's say phi equals 0. So it means that t equals 0, it's going to be here. Okay, so the velocity is here. Then it's going to be here. So you're going to have minus a omega sine omega t. So you see that when t equals 0, the velocity, it's going to be 0. It makes sense, because if you look here, you start from here at t equals 0, you have your stopwatch, and it's not moving, so the velocity equals 0. If phi equals 0 here. Now you see that at t equals 1/4 of the period, so it means here, so it's been moving, it's going through its equilibrium. So if it's 1/4, the velocity equals minus a omega. That's going to be sine. That's going to be 2 pi. Then you have t times t over 4. That's going to be minus a omega. That's going to be sine of pi over 2. That's going to be 1. So you see, in that case, V is going to be V max, and it's going to be minus a omega. So when it's going through the initial position, after 1/4 of a period, the velocity is to the left and it's maximum. And again, you look at this projection here on the screen. Okay, so here we are half of the period, right? So half of the period, so the velocity is going to be minus a omega sine, and then you have 2 pi over t times half of the period. You see sine of pi is 0. So that's going to be 0. So half of the period is going to be 0. Okay, so we are here. Okay, so we are here, right? So at that point, it's there is no component, there is no x component. It's just pointing down. Okay, so we can keep going. At 3/4 of the period, it's going to be minus a omega sine. That's going to be 2 pi. And then here it's going to be 3/4 of the period. And then you have sine of 3 pi over 2. That's going to be minus 1. So you have the velocity, which is V max again, but now it's positive a omega. So that means when it's here, it's also maximum velocity, okay? But it's positive. And then it's coming back here. Finally, when you have t equals a full period, so you're going to have minus a omega sine 2 pi t times t, and sine of 2 pi equals 0. So we are back here. So just for you to understand how it works with the sine and the cosine. Okay? So what about the acceleration? So about the acceleration, when t equals 0, it's going to be here. Acceleration depends on the restoring force. So at t equals 0, you have maximum acceleration because you have a maximum restoring force. After 1/4 of the period, there is no acceleration because there is no force. Force and acceleration are always proportional to each other. Then it gets to here. Again, the acceleration is maximum, but now it's positive. Here it was negative. Going through equilibrium, here the acceleration is 0, and it's because the restoring force is 0. And then acceleration is negative. So you see acceleration and the velocity are out of phase, okay? When the acceleration is maximum, the velocity is 0. So you can also see that with a circular motion. So with a circular motion, remember that if the speed does not change, so here we have a constant speed, the acceleration is a centripetal acceleration. So it's pointing to the center. And if you look at the x component of the acceleration, that will be your acceleration here of that oscillator. And again, I think I show you this great simulation. I don't remember where I found them. So you see here, it's a circular motion. You have a centripetal acceleration toward the center, but if you project on the screen, you find your simple harmonic motion, with the restoring force being maximum at the top and at the bottom. See? And here at the center, at the equilibrium, there is no more acceleration. Isn't that a great simulation? So if you back to the slide, that will be the expression for the acceleration. Okay, so we have again, so the displacement is A cosine omega t. I'm going to forget about the phi. So velocity equals minus A omega sine omega t. And this is your Vmax in magnitude. Now to get the acceleration, I need to derive again. Okay, acceleration is dv over dt. So I have to take the derivative. Derivative of sine is cosine, so it's going to be minus A. Take this one out, cosine omega t. Okay, so if you do t equals 0, you see the acceleration will be maximum, but to the left, which makes sense here. At t equals 0, the acceleration is maximum, but it's negative. Then when you have t equals 1/4 of the period, it's going to be minus A omega 0. And then I'm going to have a cosine. So if you plug in, you're going to have pi over 2. That's going to be 0. Right? So now I am here. There is no acceleration along the x-axis. I am here. There is no acceleration because there is no restoring force. And then you have t equals half of the period. That's going to be A equals minus A omega squared. You're going to have a cosine. That's going to be pi. Right? And pi, so the acceleration will be positive and maximum. So it means at that point here, acceleration is again maximum, but it's toward the right. So I am at that place here. Then going 3/4 of the period, so the acceleration, it's going to be 0 again, because it's going to be cosine of 3 pi over 2, so that's going to be 0. So I am here. No acceleration, no restoring force because there is no stretch. And then at the period t, acceleration is again minus A omega squared. Okay, so I have x, I have v, and I have the acceleration. So what's interesting is that if you compare both of them here, you see that the acceleration equals minus A omega squared. Okay, so cosine omega t. So A equals minus omega squared. And this is your displacement x. So we have acceleration plus omega squared x equals 0. And we find again our equation of motion, right? So we derive that by saying F equals minus kx for a string, for example, equals ma. So you have A plus k over m x equals 0. So acceleration plus omega 0 squared x equals 0. So this is the equation, differential equation, second order of a simple harmonic oscillator. And sometimes even a pendulum will follow that equation. So what that means here, it means that this solution here, this displacement is the solution of that differential equation here. So each time, even in math, even if you are not doing physics, each time you have a differential equation with acceleration, something here, x equals 0, so you know that the solution could be a cosine omega t plus 5. Or it could be also sine, or it could be a sine plus a cosine. All those will be solution. So this is the equation for a simple harmonic oscillator. Okay, so we just prove that. Okay, let's see what is next. So I have problems. Okay, so here is just a review. That's the different way to write exactly the same thing. That will be the differential equation, the equation of motion that describe a simple harmonic motion. And you see in that case here, it's a spring. So that will be the angular frequency, which is also called the natural frequency. It means if you stretch the spring, it wants to oscillate at that frequency, only that frequency. Okay? And you have the solution, which is a cosine or a sine. So this is a displacement here. Let's say it's a cosine. Okay? So here you have the graph. So you have the displacement here. And if you take the derivative of that, you're going to get the velocity. And you see, this is a cosine. Take the derivative, you get a sine. Take the derivative, you're going to have a cosine again, but there will be a minus with this one and that one, right? So this one is cosine omega t times something, and this one is minus cosine omega t times something. So I don't know if I say it right before, but you see that between the displacement and the velocity, if you compare both of them, they are 90 degrees out of phase, meaning when this one is at this peak, at its peak, the velocity equals 0. This is because if you take the slope here, the slope, you see it's flat, so the slope equals 0. At that point here, the slope is negative, but it's also maximum. So that's why here you have a maximum, but it's negative, or you have a minimum, more like this. So here again, displacement here is maximum in magnitude, so it's a minimum, but the slope equals 0, so the velocity equals 0. Here, the slope is maximum, it's positive, so you have a positive positive velocity, and it's a maximum. So those two are 90 degrees out of phase. And those two here are again 90 degrees out of phase, meaning when the velocity equals 0, the acceleration will be max in magnitude. When this one is max in magnitude, acceleration equals 0. So it's a 90 degrees out of phase between velocity and acceleration. Okay, so you can take the time, pause the video, and analyze that. Now let's go to some problem, not calculus, just algebra based. So this one is actually interesting. It's a typical problem, but I'm going to do that at the end. So let's try to apply what we have learned. So so those problem comes from Wolfson. It's a physics book, and it's Wolfson. It's called Fundamental Physics. So it's also a very good book if you want like a summary. You don't want to have too much explanation. So it's just a summary. So it's a very thin book, and they have very good problem. It's called Wolfson. Wolfson is the author, and the book it's called Fundamental Physics. So that's where it comes from. Okay, let's try to apply what we have learned. So what did we learn? We learned that displacement is A cosine omega t, and then the velocity will be minus A. I have to take the omega out, acceleration, you still have the negative, and then you derive again, Okay, so you see, it's interesting because we are not talking about spring, but machine that will behave like a simple harmonic oscillator. So let's see what they give you. So they give you the amplitude 1.27 centimeters. So it's a sewing machine. Well, if you have seen those sewing machine like this, you have a needle here, and the needle go up and down. And the frequency is 2.55 hertz. So omega, the angular frequency, is going to be 2 pi times 2.55, and the unit is rad per second. So what is the maximum speed? So they don't want the velocity, they want the speed, so the magnitude. So that's going to be A. So that's easy. So it's going to be V max equals A omega. Which is, so we're going to keep centimeter. So let's keep centimeter times omega. So it's going to be 2 pi times 2.55. So unit will be centimeter per second. And we find, so you can plug it in, pause the video, and that should be 20.3 centimeter per second. So B, maximum acceleration. So that will be this, right? So it's going to be A omega square. So that's going to be this. So it's going to be 20.3 times another omega. So it's going to be times 2 pi times 2.55, because you have to multiply by omega again, and you get 376 centimeter per second square. So you have to do it to check on your own. No, 225. So 225 centimeter per second. Okay. So next one is interesting because it's showing you why sometimes it's easier, or it helps to make the circle, to visualize what's going on. So you're gonna see why. So for this one, you have different way to do it. I don't know if I've done it. How to move this one? No, I want just to move it here. So here we have the frequency and we have the amplitude. Okay, but at t equals 0, the object is at x equals 0. So it means t equals 0, x equals 0. So what does it mean? So let's take the circle, right? That's going to be my x-axis. Okay. Here I have my amplitude, which is 0.12 meters. And it's going in this direction. And it's going to tell you that at t equals 0, maybe it's going to be here. Or it could be here. And it's moving in this direction. So it means if you take the oscillator, okay, so it means it's oscillating between this position here. That position here is 0.12. That should be your equilibrium. That's going to be minus 0.12. So it's oscillating back and forth, but we start the stopwatch here, t equals 0. Okay, so you have the easy way and the long way to do it. And so at t equals 0, it's either here or there. But it says how long does it take the object to go from x equals 0 to 0.048. So 0.048, it's somewhere there. So that means you can take your object here, and then the next, that means it's moving here. So it's going from here to there, right? So it means my object was here, and now it's there. So it has moved. The displacement here along the x is 0.048. So my point is that if you take your cosine, so if you say that your x equals a cosine omega t plus 5, so at t equals 0, it must be here because the next, it's going to be there and it's positive. Otherwise, if I am here, the next position is going to be negative. So that's why it's good to have that circle to help you out so you can visualize. So what does it mean? T equals 0, x equals 0. So that means you plug 0 inside. So that means x equals 0 equals a cosine phi. So that means phi has to be either pi over 2 or minus pi over 2. And since I have decided that it's going to be here, then it's going to be negative pi over 2. So my displacement equals 2. I have a 0.112. I have a cosine, have a omega. So omega equals 2 pi times 9.7. So omega t minus pi over 2. Okay. So from here, you have two choices. You keep that, or you remember that is the same as 0.12 sine omega t. Okay, because cosine, if you have an angle, cosine, let's say you do cosine 90 minus 30 minus 90 degrees, you're going to see it's the same thing as sine 30. You can verify with your TI that it is true. So if you do it this way, it's going to be much easier, because in that case, you are just looking, in that case, you are just looking at the y-axis, right? So you are projecting along the y-axis. So you say, okay, at t equals 0, if it's a sine, t equals 0, sine of 0 is going to be 0. So you are looking along the y-axis here. Or you can say with this. So let's do the hard way. I'm going to stay with that. So x equals 0.048 equals 0.12 cosine omega t minus pi over 2. And then I have to decide if I stay in radians or if I go in degrees. So usually you stay in radians, but then your calculator has to be switched to radians, right? So you have cosine omega t minus pi over 2. Pi over 2 equals 0.048 divided by 0.12. Then you get, I think you get 0.4. Okay. So this has no unit, because yes, so 0.4, except it's in radians. So then you take your calculator and you switch to radians. So you're going to be cosine omega t minus pi over 2 equals minus 1, 0.4. So what we are looking for that angle here. So we are looking for that angle here. That angle is going to be negative here. Okay. So when you take cosine, you see that cosine for a given cosine, you have two angles. You have positive or negative. So this one, it has to be negative. So it's going to be minus negative 1.16 pad. Okay. So it has to be negative. That's why it's good to use this circle here, because I see where I am. Okay. For the same cosine, I have two angles, a positive or negative. It has to be the negative one. So omega t equals minus 1.16 plus pi over 2. And I didn't do it, so I'm going to do it. So you do that, and then you solve for t, and that will be your omega here, right? So you do minus 1.16, okay, plus pi divided by 2. Okay, so that's going to be 0.41. So omega t equals 0.41. So t equals 0.41. And here you divide by 2 pi times 9.7. Okay, so divided by 2, divided by pi, divided by 9.7, and you get 0.0067 or 8 seconds. Now, this makes you think through. Now, if you start from here, of course, it's going to be easier, right? So if you start from here, so then it's less step, okay? Because you're going to have 0.12 sine omega t. It's going to be equals to 0.048. Okay, that's what I did. So sine omega t equals 0.4. So in that case, you don't have, that means the angle has to be positive, and you find t equals 0.0068 second. And it's, of course, it's easier, but it's still nice to understand what's going on. If you take the sine, that means that you take the oscillator along the y-axis here. Okay, so if you take the sine, that means your oscillator, you are projecting along the y-axis here. So at t equals 0, it's going to be here, it's going to be 0. And then you're going to move there, and you see that's going to be your sine. Okay, so the sine, there is no doubt that your sine has to be positive. Okay, because the sine of a negative angle it's not going to be the same. So of course, this will be easier, but it's still nice. It's still nice to see what's going on in a trigonometric circle. Okay, let's do the next one. Can I make it bigger? So that's going to be the amplitude here. That's going to be V max. So let's make a circle. So the amplitude here is 3.5 centimeter. Maximum speed. So maximum speed here is going to be 26 centimeter per second. What is its speed when the displacement is 1.75? So maybe it's going to be somewhere, this is 1.5. So somewhere here. So what is the x component when it's here, right? So you have an oscillator here that will be its equilibrium. Here you have maximum velocity equals 0 here. And the maximum velocity here. So it's going to be maximum velocity here at that point here. So anyway, so what do we want? We want, so Vmax, maximum velocity equals, that's a given, 26, which is equals to the amplitude. Amplitude is 3.5 times omega. So then we can find omega. So omega equals 7.43 rad per second. The displacement. So what is the speed when the displacement is 1.75? So let's look at the displacement. So it's going to be A, which is the amplitude, so 3.5 cosine 7.43 t plus 5. And at t equals 0, I suppose I'm here, so I can forget about that. So 5 it's going to be equals to 0. And we want the displacement to be 1.75 equals 3.5 cosine 7.43. So we're going to solve for this, and you have to switch to radians, right? So we have that cosine 7.43t equals 1.75 divided by 3.5. So 7.43 t equals cosine. So you take the inverse cosine. So 1.75 divided by 3.5. And it has to be in radians. So it's going to be 1.05 radians. So t equals, oh, you don't have to find t. I'm going to keep that. So that's going to be omega t. Okay. Because I want to find the speed, right? So then the speed, it's going to be the max. So it's going to be minus a omega square. So minus a, or is a. So it's going to be 3.5 times omega square. So omega, it's, omega is 7.43 square. So minus a omega square. And here we have to be careful that we have a sign, and omega t is 1.05. Okay, did I do it right? So that should be, all that should be the maximum, which is 26, so I didn't need to do that. So 26 times sine 1.05, and you get minus 22.5 centimeter per second. So the speed, they just want the speed. So that will be your speed here. See, I didn't have to do that because you already are given the maximum speed here. Okay, so that's going to be the speed here. That's all you want. Okay. So let's do number 4. Number 4. So we stopped here. So this one, I think this one is easy. So you are given the displacement, and you have 12.3 cosine 1.26 t. So that's going to be your omega. So omega equals 1.26 rad. So rad does not count as a unit. That's why you just say, you just see here s to the minus 1. Okay. And then at t equals 0.815 seconds, how fast? So v is going to be minus, amplitude is 12.3 times omega. So it's going to be 1.26. And here you have to be very careful. There is a sign here, 1.26 t. Okay, I think that's it, right? You just plug it in. Just plug it in. Plug that here. Yeah. plug that into here. So you can pause the video, try to do it, and then you should find minus 13.3 centimeter per second. So it's, you see, it's negative. So if it's negative, that means it's pointing this way, right? So if it's spring, we are back to the, so it's going to be at that position here. And then B, the acceleration. So acceleration is also minus A omega square. And then you have a cosine. So it's going to be minus the amplitude, and then omega square, which is 1.26 square cosine. Then here you have 126, and then you have the time t. And you plug the time t inside, and you get acceleration equals minus 10.1 centimeter per second. So the magnitude is this number, 10.1 centimeter per second. Okay? We're almost done with those kinds of problem. So it's not very calculus heavy, just more like algebra based. So where are we? Is that number 5? Okay, so it's a machine and it's vibrating, and you have the period here t. Okay, so if you have the period t, you have omega equals 2 pi over t, and you get 23.3 rad per second. So it's a machine, it's vibrating, and the range is 3 centimeters. So from its minimum to its maximum, it's 3. So that means the amplitude is 1.5. And that will be the x-axis. At t equals 0 is at its central position. So it means t equals 0. When you start your stopwatch, it's here. And it's moving in the x position. So that's very important. So it means it's going this direction. Okay, and it's going back and forth. What's its position when t equals 55 seconds? So again, it helps if you make the circle here. And so that means at t equals 0, it should be here, or it should be there. If we use the cosine, okay, so if you use a cosine, the magnitude is 1.5. That's going to be cosine. That's going to be 23.3 t plus 5. I know that at x for t equals 0 is going to be 0. So that means 5 equals plus or minus pi over 2. So it's either here or either there. So what do you think? But you know that it's moving toward the positive. So it means it's located here. Okay? So I have eliminated that case. So that means I can write cosine 23.3t minus pi over 2. And again, you can turn that into a sinus. Is a sine, but I won't. So what's going to happen at t equals 55 seconds? So you have to plug it in. You have to be very careful to put everything in radians. So 23.3 times 55. Inside you have to be minus pi over 2. So the best way to do it, you do first 23.3 times 5, and then you do minus, open the parenthesis, pi over 2, and then you take the cosine, you multiply by 1.5. And if you do that, you get a negative number, 1.44 centimeter. So where could it be here? But you know that the period is 0.27 seconds. So you start from here, that will be your t equals 0. Once it's going to be 0.27. So another time 0.27 times 2. So here the time is 55 seconds. So you divide by 0.27 and you get 203. So it's going to be 203 times 0.27. So it's going around 203 times. And at the end, how much is left? 0.19 seconds. So that's going to help you find out where it is, right? Because it's going once and twice and 3 and 4, 2 or 3 times. And then you have that much time left. Or that much time left relative to the period is about 0.7. So it's more, little bit more than 1/2. So it's going to be less than 3/4. So that's half of a period. That's 3/4 of a period, which is 0.75. So it means it's going to be here. Okay, so that will be here. So the machine, it's going to be at that location there, somewhere there. Okay, on its way. So it's going to be a negative velocity. And here, the displacement is minus 1.44 centimeter. So at that time here, it's going to be on its way in this direction. On its way to here. Okay, so if you make a circle, it really helps visualizing what's going on. Okay, so I don't know if I'm gonna do everything. Number 6, I think, is easy. We are not done. I think I picked too many of them. Number 6 is easy. But you see, it's not very heavy in math. If you go step by step, it's not that hard, right? So you have the x component of the velocity, so 0.45. It's meter per second now. So that's going to be the magnitude of the velocity. So minus a and y sine. I mean, there is no minus. So that's going to be the maximum velocity because there is a phase here. So sine 25.4 t plus 0.223. So that's the phase. So I don't know what they want. The amplitude. So we know that omega is 25.4, and we know that A omega equals 0.445. So that's the maximum in magnitude, maximum velocity. So A times omega is that number here. So that's going to be no, it's not centimeter, it's meter per second. And so we can find the amplitude. So it's going to be 0.445 divided by 25.4. And we get 0.0175 meters, which is 1.75 centimeter. Okay. Maximum acceleration. So it's just going to be a mega square. So you take that number here, 0.445, and you multiply again by omega, 25.4, and you get 11.3 meter per second per second. So there is no negative, but you see here there is a phase shift. So if you want to know, sometimes it's easy to see what's the phase shift in degrees. So you multiply by 180 and you divide by pi. So that's the velocity. So 0.223 times 180 divided by pi. It's that angle here is 12.8 degrees, right? So that angle here. So it's somewhere there. Okay. So in that case, you take you get positive numbers here for the phase. So you might ask, how come there is no negative? Someone asked me that. Why do we don't have negative here? That's because nothing stop you from deciding that will be the positive direction here. So in that case, even if you have an angle here, 12.18, then you still have a positive x component of the velocity. And it's going to become negative here when it gets to this side here. So that's going to be a negative component there. Okay, so what else? So this one looks tricky, but it's not. It looks complicated with a lot of information, but it's not. So you can pause the video. You have to read very carefully. So you have two mass. Okay, so one is 16 kilogram and the other one is 12.8. So it's like you have a big mass here. And it has K, it has a spring constant, and it's set in motion at an amplitude, so 78 centimeters. So the amplitude is 78 centimeters. At the instant when the acceleration is at its maximum, then that mass split apart. This mass split apart and this one stays attached to the spring. What will be the amplitude of the oscillation? So, but if you read carefully, you see that it's split apart, so you have two mass here, but it's split apart when so that was the equilibrium here when it's at maximum acceleration. So somewhere you have the center of mass. When it's at maximum acceleration, and the maximum acceleration happens when you have the maximum restoring force. So when x equals a, that's when they split apart. But you can think of that as that restoring force only depends on the spring constant, right? So if you think of energy, the energy is 1/2 Ka square here when they split apart. And there is no mass involved here. So it's still gonna keep the same energy, okay, when it's at maximum amplitude, because there is no mass involved. So even though this one is gone, you're still gonna have the same amplitude. Now, you're not going to have the same velocity here. When it goes through the equilibrium, that energy here is turned into kinetic energy. So that was potential elastic energy. All that is going to turn into energy 1/2 mv max square. So the speed is going up because the mass is going down, but the maximum elastic energy is going to stay the same because it only depends on the amplitude. And the amplitude is the same, that because that's when it's split apart. So the answer is 78 centimeter. So it looks challenging, but it was really not. So the answer is this here. So let's go back to those spring constant, because I didn't do many of them, so I just want to do 2 of them, but you have a lot of tutorials on YouTube. Lots of tutorials on YouTube. So I'm just going to do 1 or 2, that's it. Okay, so what's happening when you have a mass here and you have K1 and K2, and what do they want? They want the angular frequency. So that means they want to have omega. And the way to find omega, remember when we get to the equation, when you're going to use F equals ma, that's going to be the restoring force that wants to bring the system to its equilibrium position. When you malax and the massage, once you get to something like this, you have x here, that will be the displacement, equals 0. That here, that's going to be your omega sub 0 square for all simple harmonic oscillator. So let's see if we can find that equation here. So let's say we start from here. Here it's happy. Okay, so that will be its equilibrium position. And then now I am pushing in this direction, pulling. So now the mass is going to be here, and this one is going to be squeezed. So you see that spring here has moved by x sub 1, and this one, that spring here, has moved from, it was there and it's moved by x sub 2. So this one, it was here, and this one also has moved by x sub 2. So anyway, what you see is that the force here, you have 2 forces. You have the force from this one, F1, because it's been extended, so it wants to bring back to the initial position, and you have from that one here. So F2 here, and that should be F1. So the net force equals minus K1 X1, because if you pull the mass in this direction, that spring wants to bring it back this way, and this one is also pushing to the left. So both of them are pushing to the left. They are not happy. Yes, if you bring the mass here, the thing has been squeezed by X up to. Maybe it's easier to see that. So minus K2 X2. Okay? But you see also that X1 equals X2 equals X. Because of course, they move by the same amount. They have moved by the same amount, right? They have to. So the net F net equals minus K1 plus K2 times X equals mass times the acceleration, which is dot. Okay? So then you can see that everything happens like you have a spring constant of K1 plus K2. Okay? Or you can say X dot, which is the acceleration, plus K1 plus K2 over the mass equals 0. So that's going to be your omega sub 0 squared. And so that's going to be 7.6 plus 5 divided by 2, you plug it in. And then you take the square root and you find 2.5 rad per second. Okay? I think that's it. So I have two challenging problems that you can just skip. Okay? You don't have to you can skip the end of the video. So one challenging problem, but again, you have a lot of tutorial. USB is not recommended. So one problem is also a classical problem, and you have two springs attached to each other. So you have one which is K1, and then another one which is K2, and you have your mass here. So that's going to be your equilibrium position. And what's going to happen if you make that as an oscillator? So now I have still my X. That's going to be my 0. So both of them are going to be stretched, right? But they are not going to be stretched maybe by the same amount, because it depends on K1 and K2. If K1 is stiffer, so it's gonna resist more, so it's not going to stretch by the same amount, right? So maybe this one is gonna be X sub 1, and X2 is also, this one is also gonna stretch. So this one is stretching by X1, this one is stretching by X2, Okay? But it depends on x1, of course. And that position here is the position x. Okay? So if we look at Newton's second law, if you look at the mass, that force here acting only that mass here is just acted upon by just that force here, and that force depends only on that spring. So that force here is going to be minus K2 X2. X2 is the amount by which that spring has been stretched. Okay, so what is X? The other thing we know that X equals X1 plus X2. Okay, so the total amount by which it has been moved, it's the stretch from that spring plus the stretch from that string there. What else do we know? If you look at that point here, because there is action, reaction, so this force here will be the same as this one, and that spring here is going to pull back here. So what do we have here? We have that K1 X1 has to be equals to K2 X2. Okay? Because that, if we neglect the mass, okay, so that force will be the same as this one. So that force here will be also the same. Those forces will be equal to each other. For every action, you have a reaction. So you have K1 X1 in magnitude equals K2 X2. And then my Newton's law just apply to this. So I have minus K2 X2 equals the mass, and then my acceleration will be x dot dot, or just the acceleration in x. So that's not good, because I have an x2 here and I have an x. So I need to find a way to express x2 as a function of x. And I can look that up. I have 1 and I have 2. So let's see. I want to get rid of the x1 here, right? So I can say, so I have K2 X2 equals K1 X1, and I have X equals X1 plus X2. So I'm going to multiply both sides by K1, K1, K1. So that's my 2, and that's my 1. I'm going to subtract. So 2 minus 1. So I have K2 X2 minus K1X. That goes away. Minus K1X2. And there was an equal sign somewhere. I think the equal sign is here, right? So K2X2. Okay, that goes away. Minus K1X2. Okay, and I want, what do I want? I want to get rid of x2. I want to extract x2. So x2 times k2 plus k1, okay, equals k1x. So x2 equals k1x over k1 plus k2. So I can plug that back into here. So I have minus K2, K1 plus K2, X equals that. And that's it, because you see that's my equation of motion. Okay? So you have X dot dot plus And then you have K2, K1 over K1 plus K2. And then you divide by M. X equals 0. So that here is my omega 0 square. So that's, you can memorize it. You know, it's just, if you have springs in series, it looks like resistance. Like if you're doing electricity, it looks like resistance in series. Okay, so everything happens, like you can replace that by one spring, one big spring, and the new K equals K2, K1 over K1 plus K2. Okay, so that was the challenging one. And there is on YouTube, you have many other problems, like one which is easy. It's when you have two spring and the mass M. So that's easy. You have K1 and K2. That's easy. You can look it up, or you can do it on your own. Because in that case, you have two forces to the left, minus K1 X and minus K2 X, because they move by the same amount. And then sometimes you have more challenging one where you have one here. You have, you can have a mass, or you can have something like this. You have a spring, a mass, and then another spring. I don't think I did this one. Just forgot. So you have, but you can